Students, today we will see that what is the physical interpretation of the absence of Carnot efficiency factor in electrochemical energy conversion. As you know that in a Carnot engine or in a Carnot cycle there is a source and there is a sink. The temperature of the source is higher, suppose it is T1, and the temperature of the sink is lower, suppose it is T2. Then we know that the working material absorbs heat from the source at temperature T1 and does some work W and rejects some heat Q2 to the sink at temperature T2. So the efficiency of the Carnot engine is given by T1 minus T2 upon T1 or Q1 minus Q2 upon Q1. The efficiency of a Carnot engine is never 100% because the temperature of the source cannot be infinite and the temperature of the sink cannot be 0 Kelvin. This factor we will see in this topic that how this factor cannot be applied from a electrochemical converter. Means the concept of the efficiency is different in case of the Carnot cycle as well as in case of a electrochemical converter. In Carnot engine, the heat terms are involved, as I have just told you. Fuel cells, on the other hand, do not use the heat given out in a reaction but rather separate the reactants and make them yield equivalent electric charge. So here there is a correlation between the matter or heat and the electric charge, which then create magnetic fields and that turn the armature of a motor, etc. In a thermal reaction, the mechanism of energy conversion may be visualized that the change in energy between products and reactants is released in the form of the heat or kinetic energy of the constituent gases. These then impart upon some mechanical and movable object, for example, piston in a engine. But in these collisions, there is a series of glancing angles of incidence of the molecules on the cylinder under the transfer of momentum to the piston from the hot molecules is not complete. What we want to say here, that the molecules of the gases which are striking to the piston are at the different angles. The degree of completeness is measured by the change in kinetic energy of the particles after they have struck in the piston. Means we calculate or we must know the kinetic energy of the molecules before collision to the piston and the kinetic energy of the molecules after striking the piston. Suppose the temperature of the gases initially, that is before striking the piston, is T1, or the kinetic energy per molecule is equal to 3 by 2 K T1, where small k is, it is the Boltzmann constant and T1 is the temperature of the striking molecules before colliding with the piston. Afterwards, suppose the temperature is T2, then the kinetic energy per particle will be 3 by 2 K T2. The point is that only a part of kinetic energy, that is 3 by 2 KT1, minus 3 by 2 Kt2 was transferred to the piston. The rest of the energy was rejected to the sink. So what is the concept here? That suppose the kinetic energy of the particles before striking is 3 by 2 Kt1 and after striking with the piston is 3 by 2 Kt2. It means the difference of these two kinetic energies, that is 3 by 2 Kt1 minus 3 by 2 Kt2, is transferred to the piston, means it is used for doing the work, and rest of the energy is transferred to the sink, that is it is the waste energy which is not useful or which has not been converted into the work. Then the efficiency of the process is given by S from the Carnot cycle, that efficiency is equal to 3 by 2 Kt1 minus 3 by 2 Kt2, that is work done by the particles for the temperature difference T1 and T2, divided by the initial kinetic energy of the molecule, that is 3 by 2 K T1. If you cancel all these terms, you will get T1 minus T2 upon T1, and in terms of heat it is equal to Q1 minus Q2 upon Q1, where definitely Q1 is the heat taken from the source and Q1 is the heat taken from the source, Q2 is the heat given to the sink. So Q1 minus Q2 is the difference, that is the work done by the system or by the material divided by the Q1. So this we have converted into work equal to W over Q1 or T1 minus T2 over T1. In electrochemical converter, there are no collisions between the particles. For example, if you take the example of a fuel cell of hydrogen and oxygen that react to form, for example, water. What happens in this process? There is simply a transfer of the electrons from reactants to products. So they undergo electron supplying and electron accepting reactions on the electrodes. These electrons travel around an external circuit, and while doing so, they pass through a load, for example, the armature of a motor, and thereby do some work. Hence, there is no analog of any process of incomplete transfer of the energy difference between the two sides of a reaction to the outside of the convert as there is in thermal conversion. So what we have seen here, that in a thermal conversion there is actually collision of the molecules, but here in electrochemical conversion there is no such type of collision. Here is only a transfer of the electron from some molecules to other molecules, and these electrons, when pass through the external circuit, they produce the current. So we cannot correlate a Carnot efficient engine or a Carnot engine to a electrochemical converter. That's why the concept cannot be applied for electrochemical converters. So this is the physical interpretation of the absence of the Carnot efficiency factor in electrochemical energy convergence. This completes our topic. On next turn we will take the power output of an electrochemical energy converter. Thank you.